Hello, and thank you for taking the time to listen to our research presentation today. My name is Rochelle Moore. I am a Senior Lecturer in Fashion and Textiles at the Auckland University of Technology in New Zealand. This research is a collaboration with Professor Amanda Smith, the head of our Art and Design Department, and builds on my PhD research practice. This research explores the idea of building knitted surfaces through crafted positioning of two knitting techniques and the manipulation of the occurrent material forces. The Shimashiki digital knitting technologies are used to code and knit the surfaces. Coding constructs the knitted surface through a layering of programmed information. The software works on a grid system, with each grid a single needle movement by the knitting machine, growing the knitted surface loop by loop, course by course, or row by row. Approached from a technique-led perspective, the research engages with practice-led research methods. The knitting environment lends itself to practice-led research due to the extreme difference between two-dimensional on-screen surfaces and three-dimensional physical surfaces. Other frameworks used formed connections with concepts such as assemblage, digital crafting, the singular and the multiple, and traces of the maker and the machine. The research practice has been divided into 4 phases. However, these phases were very interconnected. My colleague Amanda Smith and I are collaborators with the technologies we create with. Often the technical must be listened to when designing, and through a greater understanding of this, our designs shift to work with the constraints encountered, rather than against. Not only do we follow the flow of the material properties, as Linda Arantes suggests, but we also follow our digital technologies during the design process. One of the knitting techniques used in this research is known as links. A links knitted surface combines back and front single jersey stitch structures to generate surface textures. Combinations of these stitch structures create multi-axial folded surfaces. The second knitting technique used is inlay knitting. This knitting technique combines the stitch loop of knitting and the weft float of weave to generate a hybrid textile. This textile is neither fully knit or weave in its material characteristics. Inlay is traditionally a technique used by hand knitters and on domestic knitting machines. However, in 2014, Shimashiki developed specialised inlay knitting machines. These machines are still not widely available in industry. However, we are very fortunate at Auckland University of Technology to have one of these in our textile design lab. The textile constructs, knit and weave, exhibit opposing behavioural characteristics. The knit component offers fluidity and multi-directional pliability, whereas the weave aspect provides an element of increased stability to the textile surface. This research looks at the positioning of these hybrid material behaviours to craft knitted surface disruptions. An opportunity exists to explore, understand, control, and manipulate the resultant material forces, fostering unpredictable, deformative surface interactions. Architecture works from the form, which is covered by a surface, whereas knitting works from the surface and can be built into a form sequentially, although this is usually as a soft textile. One aim of this research is to shift the focus for knitted textiles from three-dimensional form to the designed surface environment. A knitted surface is unique in that knitting is a built surface rather than a manipulation of surface after it is constructed. When designing a knit, you choose the yarn weight, the fibre composition, the stitch structures, the stitch quality, the machine, and how these are combined informs the physical surface. Crafting in this practice is not handmade. Instead, it references original textile making techniques that are reinterpreted and assembled as digital data. This research is positioned at the intersection of craft-based textile knowledge and digital textile technologies. Traditional weave layouts were used to translate the weave grid instructions into coded inlay patterns. The inlay prototyping incorporated scaled designs with varying float lengths to determine the effect of inlay on material behaviours and surface aesthetics. The material forces in this research arise from the stitch structures selected and the layering of the inlay yarn. Similar to the Earth's surface tectonics, compressional forces push together, tensional forces pull apart in opposing directions, and shearing forces slide past each other. Textile print repeating patterns were used to generate the links knitted grounds, providing surface distortions through the multi-directional folding. The material forces that occurred during the initial links repeats and scale testing evoked a strong visual connectivity to land movements. This connection flowed into the making process when designing larger knitted surfaces. As with natural surfaces that shift and resettle, knitted surfaces also morph each time they are touched and repositioned. They are active and dynamic surfaces. Digital programming of these knitted grounds uses a linear grid setup. However, the virtual coding decodes as physical form, and the built on-screen surface is activated into folds and twists as it is released from the knitting machine. Crafted placement of the two techniques, knit and weave, builds an environment conducive to the transference of vibrant matter into complex folds and pattern disruptions. The surface exhibits areas of weave dominance and knit dominance, generating multi-directional material force collisions. The material forces are crafted to manipulate and fracture the inlay pattern. If large areas of inlay are layered over the ground movements, this stabilizes the areas. If only small sections of inlay are programmed, the material forces below shift the linearity of the code, distorting the inlay pattern. Initial interactions with the inlay technique were self-taught, resulting in some unexpected findings, such as the yarn visibly tracing connective pathways on the surface. As author Richard Sennett notes, machines break down when they lose control, whereas people make discoveries. We viewed these mistakes as an opportunity to explore the trace connections between pattern components. The removed pathways between patterns were invisible on screen, only appearing as visible traces of the machine and maker in the physical knitted surface. Material investigations considered reactive matter using thermoreactive yarns to generate rigid forms. However, testing in larger surfaces produced less rigid reactions. The resultant surface depends on the knitting technique, the placement of the reactive yarn, the type of heat applied, and where it is applied. For the large surfaces in this practice, merino yarns were chosen, as they contain elasticity inherited from the original crimped fleece of the sheep and allowed more flexible folding to occur. We, as designers, tease out of these interactions from the materials as we allow them to have their say in the surfaces we create. What knitted surfaces articulate is changed when we alter knit design factors as well as materials. Knitted surfaces become sites of narration recording interactions between material, maker, and technology. The initial practice provided a library of design components or surface building blocks to use during the assemblage of larger knitted surfaces. Using a pick and mix system, each knitted surface is its own persona exhibiting different behavioral relationships. The surface building blocks provide an approach to design that makes knitted surface creation more accessible to a wider range of disciplines. The assemblage process which emerged utilised digital and physical aspects of making. Landscapes from my grandmother's farm in the Coromandel, New Zealand, were used as a guide for building extremely long knitted surfaces. The physical landscape is interpreted into a physical surface after undertaking several digital stages of creation. It was difficult to visualize longer lengths on screen, so a divisional grid was used to help maintain proportion between digital and physical. A collaging method was used to select the knitted grounds. Surfaces were chosen for their tactility and textural qualities. It was important to have variation between sections so that material forces shifted from horizontal to vertical and vice versa. Otherwise, the overall knitted surface appearance was too similar. The on-screen sections were filled with solid colours so that each ground pattern could be applied using a paint-by-numbers approach. Digital image adjustments were used to accentuate the foliage, providing a guide for the inlay positioning on the surfaces, and fostering a connection to the original landscape. Inlay was set up as blocks rather than as sections that interconnected. The surface building blocks contain links knitted grounds and inlay pattern libraries with the coding required to achieve the surface effect. These libraries provide a digital reference to help with the selection of material forces and building of multiple collisional surface sections. The coding affords designers the opportunity to replicate or to alter the base unit to generate their own variant of the knitted surface in the library. The practice extended to investigate building a knitted landscape across multiple interlinked surfaces. In these constructs, each panel is an individual design which feeds across boundaries into its neighbouring panels. The material forces traverse multiple intersections, and the inlay patterns track beyond the panel edges, informing a collaborative overall design. These designed surfaces illustrate and support the acquisition of material force knowledge through a physical vehicle. Surface behaviours applied material knowledge that was altered by scale, weight of the knit, and fewer material force collisions over longer distances. The assemblage of design components influenced individual stitches and the interconnected sections of the surface. The coding on screen does not display the fluidity of knitting, where the stitch structures are active participants in the creation of surface folding. As the knitted surface exits the machine, it is released from the tensions of the needle bed and the materials activate, sometimes in collaboration with and sometimes in opposition to the designer's intent. The synthesis of this practice was an exhibition of the Metamorphic series. This series of 5 panels was programmed as singular and multiple surfaces. The partial suspension of the 5 panels encouraged viewers to interact with the front and back of the knitted surfaces and facilitated the reading of surface patterns across the landscape. The partial suspension of the knitted surface also presents the material forces in 2 environments. One where the gravitational pull affects the folds, and 2 along the ground where the folds can settle. Tactility is key to understanding the hidden aspects of these knitted surfaces. Haptic encounters provide additional information to viewers as fingertips unfold and fold the knitted surface, revealing and concealing the pattern fragmentations. Each panel in the series required 9 hours to knit off and is 10 metres long when it is in a relaxed, unsuspended state. There are no repeats across these knitted surfaces, therefore each panel is a unique design and a new persona demonstrating the knitting knowledge acquired in this research. Tactility is key. Light and shadow affect the 3-dimensional textural surface and edge conditions morph the panel's linearity. The surfaces were set up to align when read horizontally, connecting the physical knitted surfaces back to the actual landscape and the digital process of making. The knitted surfaces become transmitters of knowledge, containing abstract connections to the original photographs and the making process. During this material practice, we worked in collaboration with the knitting techniques, materials and technology. Constraints encountered during the surface builds generated new approaches to knitted surface design. The knitted surfaces became sites of narration recording interactions between material, maker and technology. Thank you for attending our presentation today.